you're given a matrix of zeros and ones. You want to find the largest or the maximal rectangle within this matrix. So you can see that this is like one bar. This is a small bar here. There's another bar. There's another bar. And here is another bar. Is there any other example? Well, the other two examples are trivial. The whole matrix is either a zero. In that case, the maximal rectangle composed purely of these bars or composed purely of made up of ones is what we need to compute. So the answer here is 1 because that single one itself would make up a rectangle of size 1, since the number of rows would be 1, number of columns spanning it would be 1. 1 times 1 is 1. Here, the shaded rectangle here is the rectangle with the maximum area, because if you see here, this has an area of 4. If I cover all of, if we look at this rectangle, that would have an area of 5. This one happens to have an area of 6. So the answer is 6. So again, if we, rather than trying to think from scratch, if we were to use the solution to the previous problem, by the way, it is possible to think from scratch. I think in one of the earlier classes on arrays, I had covered a simpler version of this problem called Maximal square, where we just used a decrease and conquer approach on this two-dimensional matrix, and we were able to get to the solution there as well using linear space, but not really thinking in terms of monotonic stacks or thinking in terms of the problem that we just solved. You could, if you watch that class, you could try to go in that direction. I've actually literally spent 2 or 3 full days, multiple times, trying to extend that solution to the solution for maximal rectangles, which, by the way, needs to be done in time proportional to the size of this matrix. So if there are m rows, n columns here, this needs to be done in time order mn. But the difficulty there is that the same reasoning that we use for squares cannot be generalized to rectangles, since rectangles have arbitrary widths and heights. So just to give you, for those of you who have done that, if we try to use a decrease and conquer approach here, where we say we're going to look at each cell of the matrix, and then whenever we are at a particular cell, we'll try to compute the maximal rectangle whose bottom right point is that particular cell. That kind of thinking is one way to do things from scratch. So if I'm at row I, column j, I'm saying for this part of the matrix.
May I interrupt you?
Yes.
Yeah, sorry for interrupting. Actually, I was asking the first example you took in this kind of matrix. So you were assuming from the ground floor, right? The row that is on the bottom, and there we are considering the height that we can eventually translate that problem into the way we did the previous one, the solution, right? Left span I, right span I.
Yeah.
But if you are going to calculate the maximum rectangle or maximum rectangle or maximum square, so what is the difference in approaching between these two problems?
So let's actually talk about that. Let's actually deal with your question first, and then I'll deviate from a monotonic stack approach to see if there are other options. Well, I couldn't, as I said, the maximal square approach, which I had used in an earlier class, couldn't be generalized to this for reasons that I could get into, but let me set that aside for now. We know how to deal with this kind of a matrix and transform it into this kind of a histogram and then solve the problem. Now we have a more generalized matrix where we are not necessarily given everything at the ground floor level. But regardless of that, the maximal rectangle is going to look something like this. This is my entire matrix. My maximal rectangle is going to be some rectangle within this matrix, right? It's going to have a horizontal base and a vertical height. These will all be filled with ones. So I could interpret this rectangle as the ground floor here, as resting on a ground floor where all of these buildings, maybe some of them rise to a higher height. But some of the buildings will be at the, at this height, because that's why we couldn't extend this further up. So we can interpret this rectangle as, if you just chop off this part of the matrix, it's still, you can imagine creating a histogram out of all of these values. And this solution would be the best solution if this was the ground floor. Does that make sense? If you were to map it to this problem, where you're given a clean ground floor. You're given a clean ground floor here. And if you're given a clean ground floor, you can instantly map it to this problem we did and solve it. If you're not given a clean ground floor, you can try every possible row as the ground floor and do this mapping and solve it. Right? What alternative is there? If you know that your matrix could look something like this, a naive way to do it would be to try every possible row as the ground floor, compute the histogram, and then use the solution to the previous problem. And that is in fact what you're supposed to do. Because the best rectangle, which is going to look like this, is going to have some row as the ground floor, some row as its ground floor. We don't know which row that ground floor will be on. So try every possible floor. So we could start from the top floor. The top row, sorry. Interpret it as the ground floor. Create a histogram. Use the solution we used for the previous problem. Literally copy and paste it. See if it works. Get the best possible, maximum possible rectangle with the maximum possible area. Then add one more row. So look at the next row. Pretend that is the ground floor now. Change the histogram. Recalculate the solution. If you get a better solution this time, update the global answer. Otherwise, leave it as it is and then move to the next floor. So try every possible row as the ground floor or the ground level. Compute the histogram, or I should say the skyline. histogram, or you can say skyline, for depending on how you're interpreting this, for that ground floor. Cut and paste the previous solution into to compute a new set of local answers. And update global answer if needed. So if
this makes sense. One more question on top of it. So we have kind of, I'm not sure actually that way I can solve that. We have, so suppose that given the constraint, the number of zeros or one are very sparse or something, some kind of there in that cases, we have some way of solving this connected component problem, right? Where we go and span across and we find all the connected region. So can that also approach be helpful here in some sense? Maybe not optimal,
no,
but
so that is also the difficulty with extrapolating the maximal square solution to this, because when you're looking at a rectangle, its width and height can suddenly change just because one of the buildings in the middle happen to be shorter. So connected components does not help you keep track of the shape of the figure, which
correct.
in this case is an arbitrary rectangle. And that is
Agree.
that is the challenge here.
I see.
That's why those
Yeah, makes
approaches
sense.
generally don't work, because anyway, let me implement this and then we can have maybe a
Yeah, sure.
more discussion on that. So is this approach clear to everyone? Given that we can, if we have the histogram for any particular row, treating that as the ground floor, it takes time proportional to the size of the length of the histogram array, which is going to be n in this case. Order n time. You want to use order n time for each option, each possible ground floor option. And there are m ground floor options. So order m in time in total. So by doing this, we can get this easily, although we will need order n space, auxiliary space. And then doing this for each row, we can get this done in order m in time in total. Now, when we go from one ground floor to the next ground floor, we want to make sure that computing the histogram doesn't take too much time. In fact, if we have the histogram for the up to the previous floor, we want to reuse it to get the histogram for the next level, because that information, the information up to the floor above, is already accumulated in the histogram. So we just have to add the information from the next row to update the histogram. So updating the histogram will also take no more than linear time that way. So that time gets subsumed within this order n. And that's how we achieve an overall complexity of order mn. So let's do this. Let's write the code for this. So what we want to do is for each floor, so what we want to do is to try every possible row as the ground floor. So for each possible floor, in English, I would say for each possible floor from row 0 to row m minus 1. By the way, m, I'm assuming, is the length of the matrix that we are given, and n, the number of columns, can be computed by looking at the length of the first row of the matrix. So that's the convention. So for each possible floor in the range from 0 to m minus 1, we want to reuse the solution for the previous problem, treating that as the ground floor. So how do we do that? Treat this row as the ground floor. And update or get the histogram array. It's called the heights array in the previous problem. How do we get the heights array? Well, when we start, we had nothing. So our heights array, in a sense, was just a histogram with no buildings in it. One-dimensional array of size n, initialized to 0. And in general, when we move to an arbitrary floor, the heights array is going to be some populated histogram, which we now need to extend to the next floor. So how do we update the heights array for this floor? Well, we go through each column. We go through each column. And if it is a 1, we're going to add 1 to the histogram. If at that particular cell, we see a 1. This, by the way, is an array of a two-dimensional array of strings or characters here. So if it's a 1, we will add a 1 to the corresponding entry in the histogram because that building just got one more floor taller. So you can say heights of column would increase by 1. Otherwise, otherwise it means there is a 0 there. What do you do if it's a 0 there? That means there is no building. There is no building at that location. So we will set the column to be 0. You can say, well, why is this necessary? If there's no building there, maybe there was never any building there. Well, that's not true, because in this particular problem, it's possible that you could have a picture like this, where when this is the ground floor, you had a building here, but then when you move to the next floor below, suddenly this becomes empty. So you would have to, reset the value here to 0. Because otherwise there would have been a finite value up to the previous floor. That has to be reset to 0. If you don't reset this, it's like assuming that this entire bar has come down by 1 floor, which is not what we want. So we need to explicitly mark this as 0. And once we've marked this as 0, Our histogram is ready. So I'm going to have a blue box here, which I'm going to say cut and paste the solution to what is the name of that problem?
Maximum rectangle.
Largest rectangle in histogram.
Largest rectangle.
Largest rectangle in histogram. The only thing that you would do there is, you have a global variable there, which will now need to be made a global variable for the whole problem here. So the global max value will just be the global max value for the whole problem this time. So you don't return it after solving the problem. So you would just move that initialization of the global max value outside the whole thing. Otherwise, there is no other change. So after the end of this for loop, you will return the global max value. Okay, so for each row, we update the histogram and then just plug and play the solution to the largest rectangle in histogram problem using 2 monotonic stacks, and you're going to get the solution, the updated solution, which incorporates that additional floor. Any questions about this? Yeah, Garrett?
I'm good.
I had a broader question.
Yeah.
What will be your thought process to use this technique? Because I believe I tried this a couple of months ago. I was using the approach from maximum square. I couldn't solve it. I was struggling. I was thinking, okay, maybe I can find like the vertical side and the horizontal side. Then I get like one skinny rectangle, one fat rectangle. And so I was going down that path and it did not work out. And your approach, I guess now that I know what you're doing, I could code it up. And I was just wondering if you have any advice as to like what would make you, well, I guess now it's obvious because we know 84. And so if you just did 84 the other day, you might think, oh, okay, I can map it. But normally this wouldn't happen.
Yeah, which is why I think this is one of the worst questions that can be asked in an interview, because unless, so this is like a problem which is very easy to get sidetracked by in the wrong direction if you are trying to solve this from scratch, like just like the maximal square problem. By the way, the maximal square problem can be also solved using monotonic stacks, but it can also be solved from first principles, like I had done in an earlier class. That approach can't be generalized because it leads to a dead end for the rectangle problem. Because let's actually go back to what I was doing earlier. Well, let me write it here only. In the maximal square problem, we were looking at an arbitrary, we're using a decrease and conquer approach where when we are at row I, column J, we are asking the question, can I get the maximal square? So maximal square is essentially the same problem. It's just that you have, you need to find a square with the maximal area instead of a rectangle with the maximal area. So there, what I had done was to ask, what is the maximal square to which my cell can contribute, right? The typical decrease and conquer thinking. And so maybe the maximal square to which my cell can contribute is this. Well, of course, if the cell has a 0 in it, it can't contribute to anything. But if it has a 1 in it, then it could contribute. But if it did contribute, then it must be the case that the cell above me must have a solution already to the maximal square problem, which covers, which is of size at least 1 less than the size of my solution. Right? So I could look at the solution of the guy above me and I could add a 1 to it and say that, well, maybe I can extend it by one more row, provided these other values are also 1. But that is also something I don't need to check from scratch. I can look at the solution of the cell on my top left. If the blue rectangle is to be the maximal square for me, then all of these values, mean values, must also be 1. And all of these red values, so if I look at the cell on my left, all of these red values must also be 1. Right? Then only I can say that all the blue values will be 1 if and only if all 3 of my neighbors have a solution that covers all the cells. And then I'm only left with my cell to look at. If it has a 1, then I can take the min of all the solutions that my 3 neighbors have come up with and add a 1 if my own solution has a 1 in it. And that's guaranteed to cover a blue square of that particular size. That was the argument there. That argument fails when we are looking at a rectangle, because if we had if I was looking at row I, column J, and let's say my maximal rectangle looks like this. Then the solution that my subordinate above would have computed doesn't have to span. So in the maximal square problem, it had to span all of these values, right? It had to necessarily span all of these values. But the solution to my subordinates problem, in this case, could be a rectangle like this. The solution to my subordinates problem here, or my neighbor's problem here, could be a rectangle that looks like this. And the solution to my subordinates problem here could be a rectangle that, I don't know, maybe it looks like this. Because now the shapes are flexible. There are 2 degrees of freedom now in terms of rows and columns. And so by looking at their solution, I have no idea, what whether most of the cells in my solution are even being covered by their optimal solutions. Whereas here I have a guarantee, because if this if the square here has a width of a particular size, then it will also have a height of that particular size. So we know that the maximal rectangle here, actually even the maximal rectangle for this neighbor doesn't have to be this. Maybe it could be a rectangle that's really tall and narrow. So that's why that approach doesn't work. It leads to kind of a dead end for this problem. And which is why I think this is a, either it shouldn't be asked, or if it is asked, then you cannot expect the candidate to solve this from first principles in 30 minutes, because this attempt, I would argue, is the natural attempt. There is no way you can just directly come up with this in an interview unless you have solved the earlier problem on finding the maximal area under a histogram, because that itself is a hard problem. And then to solve this problem on top of that requires that we need to solve this. And personally, it took me a whole day just to reduce this problem to the problem of finding the maximal area under a histogram. So this might not, I don't know if this is a satisfactory answer, Garrett, but I don't think, that's why I don't think this is a good problem to ask in an interview. You're essentially checking the candidate whether he or she's already solved that problem before or not.
Yeah, thanks. Your explanation of the rectangle does help me understand why you can't use a decrease and conquer approach. Yeah, because I was making the assumption from the maximal square, which is that the previous solution will give you at least a piece of the information for the manager to solve. But it looks like the rectangle version, that's not possible. So
yeah.
Okay.
Yeah, so you can say it is still decrease and conquer. It's just that we are falling back on a relatively naive approach where we say, well, if the rectangle looks like this, I want to, it'll have its base on some particular row. So I want to do a decrease and conquer approach row by row rather than cell by cell. So I first look at the top row, find the maximal rectangle for the top row. Then I look at the second row, find the maximal rectangle for the second row, assuming the base is on the second row, and so on. And that would lead us to essentially the same problem as trying to find the maximal area under a histogram, which itself is a hard problem. And I think it's not a coincidence that on LeetCode, this problem is numbered 85 and that one is numbered 84. So when they added this problem, they added it with the previous problem. So it's pretty clear that whoever set this problem is expecting you to have done number 84 and then you move to 85.